Hey everyone, so welcome to today's talk. I am Sagar, and today we will be looking into how solving optimization problems using linear. Uh, I guess all of you already know what Devday is, so I will skip that bit. And let's jump right into the topic. So we are going to explore how simple math techniques can help solve really complicated problems. Uh, so the agenda of the talk today is we will start with looking into some real world examples of optimization, understand a few key terminologies that are involved in any optimization techniques, and then we will see what linear programming is and how that technique can be used to solve some of the optimization problems. We'll try to get some intuition of it by looking at some visualizations, and then we will use Python and see how very easily we can solve such problems. Cool. So let's jump into our topic. Introduction to optimization. Can you guys think of any optimization problems in your day-to-day life? Like optimization things are like all around us. Any examples come to mind? Reducing commute time. Reducing commute time is a very standard optimization problem. Getting ready. Yeah, you are trying to optimize on time and getting stuff done quickly. Good example. Okay. Yeah. So you guys get it, right? So it's all around us. You're trying to optimize for a certain goal in your day-to-day life. I have a few examples created. So I will quickly walk through some of those examples. Every example is different in some way. So we'll quickly run through them. The first one is the example which you shared is the commuter problem. It's a TFL map, and every day if you are trying to go from one location to another, you are trying to optimize for different things. So let's suppose you're standing at King's Cross and trying to get to Wimbledon. How do you get there? One route could be you jump on Piccadilly line, get to Green Park, change to a district line, and then finally reach Wimbledon. And one might ask, what is the best route to get there? Best is again subject to what your ultimate goal is. Is your goal to reach the fastest in the least amount of time, or your goal could be a route which has least amount of changes, or a route which leads to like least amount of walking, or sometimes you might want to avoid buses, etc., etc. So you get the point. Like based on your goal, you are trying to optimize for different things. So every time you're trying to optimize, there will be certain goal associated to it. The next example we have is of a forensic sketch artist. The artist is trying to sketch a portrait of a suspect, and there's a eyewitness who's trying to describe the details of that suspect, and then the artist is trying to build that image. He won't get the image right away, so the technique that he will use typically will be an iterative one. So we'll start with the general shape of the suspect, then start adding details like maybe what's the length of his hair, how are his eyes, how wide is his nose, etc., etc., and then keep on adding details till he achieves the final goal where the portrait looks very similar to what the suspect might look like. And this is a very iterative process where you constantly take feedback from the eyewitness and try to build that portrait. Then we have another example of ant colony optimization. Many of you might have noticed outdoors when ants are trying to get to a food source, they are probably in most cases taking the most optimal route. Now, ants definitely don't have access to Google Maps or any GPS technology, but still they are able to solve such optimization problems. How do they do that? So ants typically will start out randomly. They will take various random paths and trying to get to the food source. But when they are traversing a path, they sort of deposit a chemical called pheromone along the path. And the general tendency is the other ants will tend to follow a path with stronger pheromone smell. Now, over time, the shortest path will get reinforced because more and more ants traverse that path more quickly and more often, hence increasing the pheromone concentration along that path, and eventually all the ants will follow that shortest path. So even without using any math or any GPS technology, they're still able to solve such optimization. And there are actually various nature-inspired optimization techniques out there, which are actually being built and used to solve optimization problems. So now that we have a general idea about what different types of optimization can be done, we'll take an example and try to understand a few different key terminologies that are involved. So a farmer has 1,000 feet of fencing and wants to fence off a rectangular field that borders a straight river. She needs no fence along the river. What are the dimensions of the field that has the largest area? Given this problem, if we try to visualize it, what we basically are seeing is there's a river on one side and there's a field on the other side. The farmer's ultimate goal is trying to maximize the area of a rectangular field. Now the rectangular field has sides x and y, and the ultimate goal of the farmer is maximize this area, which would be represented by equation xy. Although given this goal, it is also subject to a few constraints. The main constraint that the farmer has is he only has 1,000 feet of fencing. So the perimeter of the rectangular here would be x plus 2y because you don't need any fencing along the river. So if you were to represent this optimization problem mathematically, the way you would represent it is the goal of this optimization is to maximize the area, which is represented by equation f equal to xy, subject to constraint of x plus 2y equal to 1,000. Make sense? Now let's try to change this problem a bit, and we'll try to see if reinforce some of these terminology. So a farmer plans to fence a rectangular pasture adjacent to a river. The pasture must contain 245,000 square feet in order to provide enough grass for the herd. What dimensions will require the least amount of fencing if no fencing is needed along the river? Now we have changed the problem a bit. Anyone wants to take a stab at what the goal is right now? Exactly. So reducing the fencing that is needed. And do you want to take a stab at what your constraint is?
The area has to be
at least 245,000. Exactly. So in this case, now your problem has become sort of the reverse. You're trying to minimize, you're not trying to maximize, you're trying to minimize the length of your fencing, which we have already established in this case is x equal x plus 2y, and then subject to constraint of area, which is xy, should be equal to 245,000. So any optimization problem will either be a maximization or a minimization problem. It will have one goal, or in optimization lingo, it would be objective function. So it will be a maximization or minimization problem. It will have one objective function and it will be subject to one or more constraints. So now that we have learned a few key terminologies, I'll quickly also brush through some other terminologies before we jump into linear programming. So most of you might already be aware of these, so I'll quickly brush through these. So what's the minima? So given this equation y equal to x minus 5 whole square, if you were to plot it on a graph, it would look something like this. Now, if I were to ask you what is the point on this graph where the value is lowest for this equation, intuitively, you would say somewhere around here, where x is equal to 5, your y is 0. Similarly, if we were to flip this problem, what's the maxima? So I have an equation y equal to 25 minus x square, which is plotted the other way around. Here we are trying to find the value which is highest on this in this graph. It would be somewhere around here where x is 0, your y becomes 25. Now both of these equations had two variables and was very easily represented on a 2D graph. But what if we introduce more variables? Now we have a third dimension introduced. This is the equation, and the surface plot of it looks something like an inverted dome. Again, if I were to ask you where is the maximum point on this graph, intuitively, it would be somewhere around here. where x is possibly 0 and y is also 0. Somewhere around that on the z axis, the maxima would be here. Although it is becoming a bit complicated than the previous one, but it is still a bit straightforward. Now let's take it one step forward. Now we have another equation, and the surface plot of this is looking very different, and there are various peaks and valleys in this graph. So there is no one highest point or one lowest point, just directly looking at this graph. So for example, if you were standing on this peak somewhere around here, from your vantage point, the minima might be here. So the minima, although you are right, it is a minima, but in the overall context of the value, that is not the lowest point, and your overall lowest point probably is somewhere around here. So this is basically the concept of local minima and global minima. So local minima is a point which is lower than all your nearby points, but global minima is the lowest point overall in the entire domain of your function. And the reason why I wanted to introduce these topics is typically when you're trying to use various algorithms and solve optimization problems, many a times your solution might get stuck into your local minima and you're not reaching the global minima. So you need to keep these things in mind and try to get to the global minima. Now that some of the key concepts are clear, let's move on to the next thing, which is the classification of optimization techniques. Broadly, optimization techniques classify into two sub-buckets, which are deterministic and stochastic algorithms. Deterministic models are basically given a problem. If you were to solve it 10 different times, every time you will get the same output. So it are deterministic in nature. And there are various techniques within deterministic, linear programming being one of them, which we are going to look at it today. There are other techniques like non-linear programming or gradient-based and non-gradient-based algorithms. Apart from deterministic, there are also stochastic algorithms, and stochastic algorithms by the nature of it have some randomness to it. So flip to the deterministic one, the same problem if you are solving 10 times, every time you might get a different result because by nature it has some randomness to it. So the output is not guaranteed and you might receive different output every time. There are various different heuristic, meta-heuristic, and learning-based algorithms that fall under this bucket. Various nature-inspired algorithms. The one that we saw at the beginning of the talk, the ant colony optimization, is a type of stochastic model. And there are various other such nature-inspired algorithms. Genetic programming or genetic algorithm is one such one, which we had used in one of our projects. Probably a topic for another talk. Cool. Now that we understand what different techniques might be, we will jump into linear programming, which is our main topic for today. So linear programming is a mathematical technique that uses linear equations to find the best solution to a problem. Now it was first applied in 1930 by an economist to solve the resource allocation problem. Although it's a mathematical technique, the first time it was used to solve an actual problem, it was used by an economist. And then since then, it was also used widely in World War II by US Air Force, again for solving some resource allocation problem. And since then, this technique is very popular to solve various types of techniques, various types of optimization problems. To understand linear programming in detail, what we will do is we will take an example. We will see how one can represent that problem in linear equations. We will plot those equations on graph, and then the same thing we will see how it can be solved using Python. So let's jump. So you have a farmer friend who has presented you with a problem for the upcoming planting season. Your friend has 3 tons of potato seeds, 4 tons of carrot seeds, and 5 tons of fertilizer. And the fertilizer need to be used in 1:1 ratio. So basically, if you choose to plant 1 ton of potato, you should also use 1 ton of fertilizer along with it. Now, what he also says is for every kg of potato that you plant, you will get a profit of 1.2 pounds per kg. And similarly for carrot, you will get 1.7 pound per kg as a profit. Your goal is to maximize the profit. Simple enough. Now, given this problem, how would you represent it in your linear equations? What you would do is you would define two variables to represent what is the quantity of carrots and potatoes I should plant. Here I am representing them by XP and XC. XP is the amount of potatoes I should plant, and XC is the amount of carrots I should plant. It's difficult to plant negative seeds, so XP and XC should be greater than equal to 0. That becomes your first constraint. Then we say we only have 3 tons of potatoes, so XP should be less than equal to 3000. Similarly, XC should be less than equal to 4000. Then we have a final constraint that the number of potatoes and carrots that I should plant should be less than equal to 5000, because that's the amount of fertilizer that I have and I'm using it in the 1:1 ratio. And finally, I'm trying to maximize my profit. Now, in this case, the profit equation will become 1.2 multiplied by the amount of potatoes I plant plus 1.7 multiplied by the amount of carrots that I plant. Cool. So we have two variables, a few constraints, and then our final objective function. Now let's try to visualize this. So I will quickly open this link. Let me move this here. So what I've tried to do is the same equation that we saw on the slide. I've written it down over here in this utility. What I'm saying is X is going to be representative of number of potatoes that I want to plant. I'm saying it is greater than 0 and less than 3000. If I were to plot it on a graph, X is represented on like the X-axis, it should be less than equal to 3000. Similarly, Y, which represents carrots, it should be less than equal to 4000. Now the overlapping region between these two lines is your feasible set. So any point within this shaded region, the overlapping region, is a point which is feasible. It adheres to all your constraints. Any point outside the overlapping region is a point where it violates one or more of your constraints. Okay. Then finally, we have the constraint of the potatoes and carrots should be less than equal to 5000, which I were to plot, look something like this. And now your feasible set has shrunk down further. And finally, our equation of the objective function, which is your profit line, looks something like this. Now, our ultimate goal is to maximize the profit. So perpendicular to this line is the direction which will help in maximizing or minimizing. So for example, if I'm trying to maximize, I will try to move in this direction, but if I'm trying to minimize, I'll try to move in the opposite direction and try to find a point within the feasible set which gives me the maximum value. Now, because we are trying to maximize a profit, we can keep going along this line till we are within the feasible set region. So at least one point on this objective function line should be within the feasible set region. So for example, if I go much beyond, I reach this point. At this point, my profit is 8,400. But what I've done is I'm planting 1,333 kilos of potatoes and 4,000 kilos of carrots, which means I'm violating the constraint that I only had 5,000 kilograms of fertilizer. So I need to find a point which intersects the feasible set and the maximum point beyond which we will go outside the feasible set. And the point in this case is somewhere around here, because any point beyond this, we will go outside the feasible set. So basically it says X is 1000, so potatoes you should plant 1000 and carrots you should plant in 4000, which will give you a profit of 8000. Any doubts here?
How can we get the value from green line? So when you move it a bit down,
yes,
it means that we can have any result
yes,
in the feasible area.
Correct.
So we can take any value of the green line,
yes,
and it can be our output.
Yes.
But we can do better.
Yes, exactly. So any point on this line is actually a correct solution. It is a feasible solution. It is adhering to all of your constraints, but it's not the maximum value. You are trying to find the maximum that you can get, the profit that you can get. At any point, if you were to choose this point on this line, you would plant your potatoes and carrots in this ratio, but you're only achieving a profit of 7,700. Is there a better solution out there? Answer is yes, because you can keep increasing until you figure out a point which gives you the maximum value.
So I increase this value and check whether I still in the feasible area.
Yes.
And once I exit the feasible area, it means okay.
Yes.
No way.
So how you traverse this feasible set region and figure out that value is how you solve linear programming. And there are various techniques out there. How do you traverse this region? There are various techniques. Some are fast, some are slow, based on different things. Traversing this region starts becoming a bit complicated. We will look at some examples. Like in this case, we only have two variables and a few constraints. So you can at least visualize this. As we will go on, you'll see that this starts becoming difficult even to visualize it. But I wanted to keep things simple so that we get some intuition about what are the key things getting involved and how you get to a optimal solution. Yes. Yes. So, there can be. So the nature of linear programming is all of your constraint and your objective function should be linear. So basically, if you were to plot it on a graph, it has to be a straight line. It cannot be a curved line. So if your constraints or objective function becomes curved line, you cannot solve them using linear programming. And there are other techniques to solve such problems. Linear programming will only be able to cater to as long as your constraints and your objective function are linear. So we've seen the optimal solution in our case was 1,000 kilograms of potatoes and 4,000 kilograms of carrots, which gave us a profit of 8,000 pounds. Now that we have seen it being solved on a graph, let's try to see how you can solve it using Python. So I have this solution implemented using Python. We are using a library called PuLP. PuLP makes it very easy to represent or formulate the problem the way we have seen it in terms of your variables, constraint, and objective function. And it also allows you to plug various different algorithms to traverse that feasible set and find out an optimal solution. So we'll see how you can represent that formulation that we saw earlier into your Python code. So to start with, I have represented a few constants in our case. So profit for potatoes, our multiplier was 1.2, and for carrots, it's 1.7. Then we had some seed limits. Like for potatoes, we had a seed limit of 3,000, and for carrots, we had 4,000. And finally, we had an overall fertilizer limit, like the fertilizer that's available to us, it's 5,000. Now, if I were to go back and show what we had done, we had defined variables and then the constraint. So we will do the same thing using PuLP. So we will define our variables. The way you define variables using the PuLP library is using a method called LP variable. You give it a name, and then you can provide lower bound and upper bound. We've already established you cannot plant negative seeds, so our lower bound for both of these variables is 0. So you define the two variables. Now our optimization problem was a maximization problem. The way you would represent it using PuLP is you'll use something called LP problem, give it a name, and then say LP maximize or LP minimize based on what your objective is. Now to this problem, you will add your objective function. So our objective function in our case was the profit multiplier for potato multiplied by the number of potatoes that you're going to plant, plus the profit multiplier for carrot multiplied by the carrots that you plant. So 1.2x plus 1.75, what you saw, is represented in this way in your code. once we have defined the objective function, we will also add all of our constraints to this problem. First one being potatoes should be less than equal to the seed limit for potato. Carrots should be less than equal to the seed limit for carrots. And then the potatoes and carrot that you plant should be less than equal to the total fertilizer that you have available. Straightforward? Yes. So the way we have defined the constraint here, you could have also done it directly in this line. Instead of 0, you could have just added 3000 here. That's another way of representing the same thing. No, you can still add. For example, you could add another constraint here saying potato greater than equal to 0. You can do that. It's just a different way of adding a constraint. I wanted to just show it in the exact same way that we have represented here. So this is one way of adding the constraint.
I'm confused with Python synthesis. Can you explain to me when we plus equal? Is it like a lambda function or what?
Yeah. So what effectively happens is this library will add equations. It will formulate that problem. Right now, it's not solving it. It is just trying to define the same thing that we defined in plain text in the formulas. It is representing in some way, and its syntax is you create a problem, and in that problem, using the variable that you have defined, you add this plus equal to means to that problem, you add your objective function and your constraint.
So what's the function? Yeah? This profit, for instance, on line 23, profit potato times potato and so on. It is a function, yeah, like lambda function.
It is not actually. It's just an equation right now. Yeah, right now it's just a string and it has the variable that we have defined. So ultimately inside it, if you
We would assume their object. Their operator will be potato.
Yeah, operator. It's like a DSL first argument and the name of that.
So the profit potato into potato, returning on the what is the LP variable I'm assuming R is overridden. Makes sense to me. I just can't understand what construct of Python it is.
yeah, for this particular thing, like there's a mechanism where you can print what it is doing. And if you look at the output, it will actually have those equations. And when I'm doing problem.solve, right, what it does is this equation that you've constructed, including the objective function and your constraint, it will pass to another library which actually does the solving of it. So it's a way of representing the problem, and then you pass it on to another library which actually does the solving part. So actually traversing that feasible state region and figuring out the solution is done by a separate library. There is a solver which is default baked into PuLP, but you can use various solvers which are out there. I will talk about various solvers later in the talk. But basically you can plug and play with different solvers. It just represents the problem in a DSL effectively.
Constraint is still okay, the objective is.
So the way it differentiates between the objective function and so like if you look at the equation, everything you're doing plus equal to and giving it an equation. The way it differentiates between an objective function and a constraint is objective function won't have a right hand side value. So this is an equation, but it does not have a right hand side value. But whereas your constraints have a right hand side value. So that's how it differentiates between your objective function and your constraints. Cool. Finally, I do problem.solve, which will take care of actually solving the problem, and then I'm printing the result. What I'm basically doing is I'm printing the status of whether it was able to solve this problem or not, and then I'm printing the number of potatoes or carrots that I wanted to plant, and what is my overall profit, my objective, which is in this case my profit. So let's quickly run this and see what our output looks like. Cool. So we have our solution available. Status, it says as optimal, so it was able to figure out a solution. It's saying the potato seed that you should plant is 1000, carrot is 4000, and your maximum profit is 8000, which we have already seen using that visualization. Simple, very easy to represent the same thing using PuLP, and you do problem.solve, and it's able to solve this problem. Now,
do we know any details about like what algorithm is using this one?
so there are a couple of techniques. There's a simplex method. There's branch and bound. I'm not going to dive deep into how mathematically you traverse that region for today's talk, but there are solved problems like how you can traverse that region. There are various techniques for that. We are using a solver which might choose one of those methodologies. But yeah, for this talk, I'm skipping that bit. Cool. So we've looked at this simple example where we had a couple of variables and very few constraints. And our feasible set looks something like that. Now, if we start adding a bit more constraint, your feasible set will start becoming a bit more complicated and it will start contracting or taking a different shape. Now, if you add even more variables, now it doesn't remain a two-dimensional thing. It will take different geometrical shapes. And as you can already see, the shape is now becoming a bit complicated, and figuring out a solution directly intuitively, it starts becoming difficult. So the more and more constraint you add and more variables you add, figuring out the solution starts becoming complicated. Let's also look at a few different constraint types. Now, in our example, the output that we got was 1,000 kilograms of carrots and 1,000 potatoes and 4,000 carrots. Now we got lucky, but we could have also gotten an output saying 123.75 kilograms of carrots, which in this example probably was fine. We could actually plant this fraction of carrots. What if you were trying to figure out how many carrots should I use while planting? Now you cannot obviously take half a tractor. So in that case, your variables should become an integer variable. So it can only take whole number values. It cannot take fraction values. Sometimes you also want to make a decision whether you should plant carrots at all, whether you should plant or skip it completely. So to make some of those decisions, your variables will need to behave binary. So take 0 and 1 value to make yes and no kind of decision. And when your problem has multiple types of variable types, including integer, binary, and continuous, your problem is no longer a simple linear programming problem. It's now takes the shape of mixed integer linear program. And when you introduce integer variables and binary variables, solving that problem starts becoming exponentially difficult. So traversing that region starts becoming even more complicated. To show how you represent the binary variables in your mathematical equations, I will quickly take an example of knapsack problem. Most of you are already aware of knapsack problem, so I will quickly brush through it. The reason why I'm taking this problem is to see how you would represent them into equations. So you have a bag which can hold 5 kilograms of items, and you have various items available there. What you're trying to maximize on is maximize the price of item that you're going to put in this bag. These are the items that you have. For some reason, you have a 1 kilogram of watch, which has a value of $50. 1 kilogram of headphones, $100, etc., etc. So you have all these variables, and what you're trying to choose is you're trying to choose items from this to maximize the price. Now, if you were to represent them into your mathematical equations, what you would typically do is for each of those items, you would create variables. All of these variables can take a value of 0 or 1. So either you pick that item or you don't pick that item. So effectively, if you want to try to maximize your price, what you will do is price of each item multiplied by that variable. So 50B1 plus 100B2 plus 10B3, 1000B4 plus 10B5 becomes your maximization equation. And it is subject to constraint that the total weight of the item should be less than equal to 5 kg. The weight of each item multiplied by that variable is less than equal to 5 kg. So effectively, if you decide to choose B1 and B2, your total value will become 50 plus 100 plus all the three variables are 0. So your price becomes 150 and your constraint becomes 1 plus 1, 2 kgs, and all the other ones are 0. So 2 kg items which are weighing 150. And you can do better. We can find a solution which is better. You get the idea. So basically, you are using binary variables, multiplying it by the variable that is represented to make a decision whether you are picking that item or not. So now that we have roughly understood how you can use this variable, I will be extending our original problem of farmer's problem, extending it to a multiple mixed integer linear programming problem, adding a lot more constraint and a lot more variables, and see how we can solve the same thing, like a mixed integer linear programming, using the same PuLP library. It's going to be very similar to what we have already seen. So now our farmer's problem has been extended. So we want to decide which crops to plant in what quantities to maximize profit. So our ultimate goal is still to maximize profit. Given limited resources such as labor, land, fertilizer, and equipment. Each crop has its own profit. It has some initial setup cost and resource requirements. My goal is to maximize profit. So let's take a look at what exactly do we have. So the number of plants that are available to us have now increased from potatoes and carrots. We have also added tomatoes and lettuce. Our decision variable is how many kilograms of each plant should I plant. And we have some parameters for each plant. So there's a setup cost associated to each plant. So if I do decide to plant tomatoes, there is going to be some cost associated to it. Now this cost will affect our overall profit, because if we choose to plant that, we will need to subtract that setup amount from our objective function, which is the profit. Profit per kg similar to the before. Then fertilizer use per kg. Previously, we only had 1:1 ratio. We are going to change that now. Labor use per kg. So more labor might be needed for potatoes, but for lettuce, I don't need that much labor. So that's going to be represented in some way. Again, land use per kg can be different for different crop type. There's equipment use. So some plant types might need some special equipment, whereas others might not need any special equipment. And then finally, the maximum allowed limit of each plant, similar to before what we had. On the overall resources, we have only a certain amount of fertilizer, labor that's available to us in terms of hours, the total land area that's available to us, and the number of special equipment that we have available. So now we have extended our previous problem, and let's see how we can represent this problem using Python and how we can solve it. So I will be jumping into this file, which is going to represent this our extended problem. So I am adding this array to represent all the crops that I have available with me. And I have these various dictionaries defined to represent each of the multipliers effectively. So the profit multiplier for each crop type is defined here. Setup cost is different for each crop type. Fertilizer use can now change. It doesn't need to be in 1:1 ratio. Labor use is again changing for each crop type. Some needs more, some needs less labor. Similarly, some need more land, some need less land. Some of the crops need equipment, which is represented by 1. Some of them don't need an equipment, which is represented by 0. And then I have a seed limit for each crop type. Then finally, I have only certain amount of fertilizer, labor, total land that's available, and then the total number of special equipment that I have available. Now what I'm going to do is, because now my variables are going to increase. Previously, we only had 2 variables. The way we had defined it was using something called LP variable, and each variable we had defined it on a new line. Now, what if your variable start keeps on increasing? So there's a helper method which is provided by PuLP, which uses LP variable.dex, which you can pass an array. So in our case, the crops array, which is representing of all the crops, we pass. So it will create all the variables for all crop types. This is going to represent what amount of crop we plant. Now this is crop planted is the binary variable to represent whether we should plant that crop or not. So this is a yes no kind of decision, and the way you define it is you do category equal to LP binary. This can take form of LP binary, LP continuous, and LP integer. By default, it is LP continuous, which means it can take fraction value. So this one, we are defining it as value, so it will only take a 0, 1 value. Finally, same as before, we define the LP problem, and again, it's a maximization. Let's look at our objective function. Our objective function is going to change slightly. So I'm going to loop through all of my crops. For each crop type, the profit multiplier multiplied by the amount of crop that I plant, the same as before. But now I'm also going to subtract the setup cost from it. So if I do decide to plant potatoes, I need to subtract the setup cost for it. And I am multiplying it by this binary variable, which is the age crop planted. So for example, if I completely skip to plant potatoes, this part of the equations becomes 0. Right? Because the binary variable will take a value of 0, so setup cost multiplied by the 0. So I won't subtract any setup cost for it. But if I do plant it, then I will do subtract the setup cost. And then I'm looping this for all the crops, and I use another helper method called LP sum. Yeah, so equipment is your constraint. So you only have certain amount of equipment available. Your profit equation is the profit for per kg multiplied by the kilograms of that crop that you plant. Right? And then you add it for all the different crops. That's what we are doing here. And the only thing that is affecting the profit in this example is your setup cost. The equipment does not have any monetary value to it. So it's not affecting your objective.
Yes, the same goes with labor, yeah? We just have a limited number of hours.
Limited number of hours.
But we don't.
Yeah, so for now, yeah, for this example, we have considered that much amount of labor is freely available to us. If we had to hire additional labor, it might cost us. We are actually going to take a look at some of those extensions going forward. But right now, the labor is available free to us. So that's why we're not subtracting any labor cost here.
So what happens if you give, I know like the library might be that's the interpretation difference between objective and constraint. Can you add like multiple objectives?
No, you will need one objective. So every, like we look like the objective, every problem, optimization problem will have one objective. That objective definition can become as complicated as like
Sure.
here you are using this equation. That equation can become complicated. As long as it is linear, you can
let's
create
say
that.
I want my thing is like I might want to increase my net profit, but I might want to do some other objective with the same set of constraints. Can I give two constraints and it will give me answers for both the objectives?
No, so if your objective changes for the same set of constraint, you will need to run it 2 different times for 2 different objectives. The same execution won't give you because you can only have one objective to your problem. Yeah, so objective definition itself, you can make it as complicated as long as the equation is linear. You have to, the ultimate criteria here is that equation should be linear. So if you can represent your problem in linearly and try to make it a bit more complicated, add more variables and try to represent it in a different way, that this thing will be able to solve it. But you cannot have multiple objectives. So we've looked at the objective definition. Let's quickly brush through our constraints. So constraint in this case, again, I'm looping through each crop type. So I'm looping through all the crops. It's basically the fertilizer used for the crop multiplied by the amount of that crop that I plant. Sum through all the crops should be less than the total fertilizer that's available. Same thing for labor use for each crop type. Summit should be less than the total labor that's available. Same for land. And finally, same for equipment available. So equipment available is for that crop type. If you need equipment, you should, and if you do decide to plant that crop, sum it through all the crops should be less than equal to the total equipment that you have available. And finally, you have a constraint for the maximum amount of that crop that you can plant. We had a seed limit for each crop type. So for each crop type, the amount of that crop that you plant should be less than its seed limit. And whether you've decided to plant that crop at all. For the other constraint, this value will take care of it. Because if you decide to plant 0 crop amount, that multiplied by the fertilizer use would take care of it. Now we have added all of your constraint. Finally, the same thing, what we do is problem.solve. So this is a MILP problem. It hasn't changed fundamentally in the way you represent it, but the way you solve it, it starts becoming complicated. But because we are using this library and using an external solver, there's not much change in the way you represent this problem. And then finally, I'm printing the output along with a few things, whether I should plant a particular plant or not. Now let's run this problem. Visual for?
Representing the plot.
The library itself won't give you a visual, but you can add like a matplotlib and use variables and plot some graph. Like I have an example, if needed, I will plot that in the end and show how you can, because when things get complicated, it starts becoming difficult to guess certain values and what's a good value, what's a bad value. So sometimes you might need to play around and test with what are some good numbers. And that time you might need to plot certain things. So already in this example, because there were a lot many variables and lot many constraints, we would have not been able to plot it on a graph, the whole solution and all these variables. And even you, like the previous example, you would have guessed that you should plant more carrots and less potatoes. But now, because there are various factors like the setup cost and land use and various things, it's very hard to guess what's the correct answer. But the library is able to provide quick answers to us. So what it's saying is our total profit now is 6,800. It's saying don't plant any potatoes or tomatoes and use these many cages of carrot and lettuce while planting. Again, as long as you're able to represent those into in form of objective function and linear equation, it will very easily solve and give you the output. All the example that we have taken a look till now are behaving like they are very straightforward. You have some numbers and they are easily represented. But in real world, you might not have like such hard constraint. You might want real world scenarios where some of the rules start bending. How do you cater to those rules? We'll take a look at next. So in real world, some of the rules will start bending, and the way you can solve those are using something called soft constraint and the concept of penalty. To understand in the context of our problem, the total land area was a hard constraint. For example, if you got up one day and decided to increase your profit, land is not something which we can easily acquire and increase the land area that's available to us. So that becomes your hard constraint. But on the other hand, the labor that was available to you, you might be able to get additional labor externally. There might be some overhead to it, like you might need to now pay additional amount to get that labor, but that is still possible. So it effectively a softer constraint. Again, you don't want to blindly go and get like just randomly get all the labor that is available, like unlimited amount of labor. Because getting labor, it is going to cost you a bit more. So that means it's going to take down your profit. So the penalties need to be carefully defined and it applies to your objective function, which in our case was profit. So what we will do is we will extend our problem further and try to understand how you can introduce soft constraint and penalty. So let me quickly check out this revision. What I've done is I've extended our problem. It's the same initial constants and the constraint that we had, but I have introduced something called penalty per excess labor. So for every additional hour of labor that I use, it will cost me 2 extra pounds. Okay. Now to represent what is the additional labor that I'm going to use, I have introduced another variable, excess labor, and I would give it in a lower bound of 0. So to begin with, I don't want to use any labor, but for every extra unit of labor that I choose, I need to subtract it from my objective function. So that means our objective function needs to change. This was our previous objective function. So the profit calculation still remains same, but what now you need to do is you will subtract the whatever excess labor that you're using multiplied by the penalty. So if you use 1,000 additional labor hours, you multiply it by 2, which will take down your profit by 2,000 pounds. That's pretty much what we have done, the change to the objective function. What we are also doing is we are making the labor constraint as a software constraint. So previously we had a labor constraint less than equal to the hard value of 5,000, what we had. But now we are saying we are extending it with the variable of excess labor. So if the optimizer while running, it might choose different values for excess labor. So whatever labor that's available with me plus additional labor is my new labor limit. Make sense? Everything else remains the same. So now what we have done is we have introduced a new variable which we have used to make one of our constraint a bit softer constraint. And we are penalizing our objective function when we increase the value of this variable. Yeah, so penalty right now, I have given it a constant value of 2.
So I think the library figure through this by subtraction.
Yes, yes. So what the library effectively does is it will apply all your variables, it will give different values. And then we'll calculate the objective function value. Run it for different values and figure out for which numbers you get the maximum profit. Now, if you increase a lot of labor, that means your profits at some point it will start going down. So beyond certain number, it doesn't make sense. And then everything is the same. Let's run this. I've also printed a few additional things like the excess labor that is used and the total penalty that is applied. Now the output, what it says is net profit of 6,800, which is the same as before. So according to the penalties and what we have configured, it cannot find another solution which, like even with additional labor, we will get more profit. So whatever we had within the limits, that's the best solution that's available. So no additional labor used, no penalty applied.
Is there a correlation between labor and?
Yes. Right now we have introduced that correlation. Before we had said that whatever the initial amount of labor was freely available to us. But what we have said right now is any excess labor that you choose will multiplied by the penalty, which in our case we have configured it to 2 pounds. It will take down your profit. So this was our previous equation of profit calculation. And we are subtracting the penalty from it.
Could you go up where the labor is?
So we have introduced this excess labor with a value of 0.
Okay, so we have the labor available in 25.
So this is.
We have a negative condition. There is an excess.
Correct. Correct.
So is there any case where we change the values? There is a case where they say, so if you use this much more excess labor, you can maximize.
Yeah, so that is what the algorithm is trying to figure out. So when it is running, it is trying to give different numbers for that excess labor variable. And it couldn't figure out a solution which was better than what we got before. So I will change some numbers now and show you how it changes your output.
Unless the labor is somehow associated with your profit.
Correct.
This won't necessarily improve.
Yeah. Like in this case, that value is affecting your profit. So that's why we are changing your objective function. But if it doesn't affect your profit,
Always reduces.
if it always reduces, then it, like, for example, in our case, if you look at the labor use is different for different crop types. So there might be a number where for a lesser penalty, you might choose to get additional labor. Right? So that figuring that number out is what you would typically do in your real world scenario. So you need to figure out what is that workable value for you. So let's take an example. For some reason, some of your labor decides to go on leave or just leave your farm. And now instead of 5,000 hours of labor, you only have 2,000 hours of labor. Now, if you run this problem, now you see your profit has come down to only 4,000 pounds, but with your penalties that you have in place, there is still no better solution available, which it decides to. So if you for some reason figure out some labor who is able to give additional hours at a cheaper rate, what if every additional labor doesn't cost you £2 but just £1? Let's try to test it out. Now I've run the problem. There you go. So now you have a higher profit. So instead of 4,000, now you have 5,166 pounds. We have used 1,166 additional hours of labor, and this is the amount of penalty that has been applied to our equation. But even though that amount of penalty was applied, we were still able to achieve a higher profit than before. So as you have seen, penalty and the penalty, the number that you choose here, it's going to be very important when you're trying to balance out your outputs. And penalty tuning is a very important aspect when you're playing around with linear programming. So what we have basically understood is not all constraints are the same. There are going to be constraints which are going to be more important than others or more harder than others. So while some constraints are soft and can be relaxed, other constraints might be harder and you will need to apply stricter penalties. Now, in this case, we only had one softer constraint. You could have multiple softer constraints, and the penalties for each of those will be different. So when solving the problem, the optimizer should try to balance out the softer penalties first and then the harder penalties. So the penalty tuning is going to play a very important role when you are playing with trade-offs. And in your typical business case, you will need to figure out which are your constraints which can be softer, whereas which are some of the other important constraints, and balance it out using the penalties. Cool. So linear programming solver. So I briefly talked about a concept of solver before. PuLP uses a solver called CBC as a default solver, which is the left one represented in this graph. This graph is representing the performance of different solvers. All of them are able to solve the problem, but it's basically how efficiently or how quickly they're able to solve. You can plug and play with different solvers. This vertical line represents, on the left-hand side of this line are all your non-commercial license, so freely available, whereas on the right-hand side, there will be some license fee associated to using those solvers. But if performance is key and if your solution is behaving low and you are okay to use commercial licenses, you can go ahead and then use one of the faster available solvers out there. Again, I want to call out all of these are able to solve your problem. It's just the amount that it takes to reach to that solution. It's going to be different, each of them. For our use case, we have mainly worked with CBC, and it has been enough for our use case and able to solve our problems. And there, we did not have a need to go to any commercial license or experiment with other solvers that are out there. So finally, when to use linear programming. So the key thing is your objective function and your constraints need to behave linearly. Only then you will be able to use linear programming. Then you want a globally guaranteed solution. If you want some randomness to it, for example, this won't provide you that output. So when you want that, you're okay with a one guaranteed output solution for every time that you solve it, you should go ahead with linear programming. And again, when you need fast and scalable solutions, you should go ahead with linear programming. There can be cases where your problem cannot be represented linearly, but you might be able to trade off certain things for a faster solution. You might be able to get rid of some non-linear constraint to get a faster solution. So in that case, you can skip some of those constraints and just jump to implement it using linear programming. In that case, you can choose this type of optimization. And as I said, when to avoid, if your objective or your constraint are non-negotiable and they behave non-linearly, you won't be able to use LP. And when your input is uncertain or is based on some probability, then again, you won't be able to use LP. For example, if your profit was dependent on weather conditions, if it is rainy, your profit is X. If it is sunny, your profit is Y. And you don't know at the time of execution. That value can be anything, and it's based on probability. You won't be able to use LP that. But if you know all of your inputs and constraints beforehand, you can easily solve it using LP. Cool, perfect. So that's pretty much that I had for the talk. Cool. Any feedback? Yeah, if you want to get access to the repository that we have, and if you want to take a look at it and maybe experiment with it, here's the GitHub repo, and the Sahaj YouTube channel is also there where you can find all your videos. Cool.
What's your use case?
Yes, so for our use case, should we stop the recording?